name is Samzile. My metric number is AN240157.
Good morning, doctor. My name is Janjali Manimaran and my matrix number is CN240340.
I am Joanne Gojia, matrix number AN240159. Now I will present about the introduction of our group assignment. Numerical methods are mathematical tools designed to solve a numerical problems that often implemented through algorithms in programming. They play a crucial role in various fields, that particularly in engineering and science, where they help in solving problems efficiently. Ordinary differential equations play a central role in modeling real-world phenomena across a variety of scientific and engineering disciplines. Differential equations can describe nearly all systems undergoing change. They are ubiquitous in science and engineering as well as economics, social science, biology, business, healthcare, and others. Among the most foundational known techniques are Euler method and the Runge-Kutta method, which offer a balance between simplicity, accuracy, and computational efficiency. The first method is Euler method, which is not numerical approximation technique used to numerically solve ordinary differential equations. This method provides an iterative approach to estimating the solution of an initial value problem by breaking the continuous differential equation into discrete steps. Euler method is the most straightforward numerical technique for solving first-order initial value problem. The second method is Runge-Kutta method. It is a major advancement in the field comes with the Runge-Kutta family of methods, especially the fourth-order Runge-Kutta method, which has become the most commonly used technique in practice. It computes four-weighted slope estimates at each step and combines them to produce a much more accurate estimate of the next value. The most widely used version is the fourth-order Runge-Kutta method, which strikes a good balance between accuracy and computational costs. Now I will present about technical and theoretical description. Numerical methods are techniques that provide approximate solutions to mathematical problems that particularly when finding exact solutions, which is impossible or impractical. They are essential in engineering, science, and other fields where complex models are used. Numerical methods often rely on algorithms that iteratively refine an approximation until it converges to a desired accuracy. Now, for the first technical description is approximation. Numerical methods are techniques that are used to approximate mathematical procedures. We need to approximations because we either cannot solve the procedure analytically or because the analytical method is intractable. For example, solving a set of 1,000 simultaneous linear equations for 1,000 unknowns. The second technical description is algorithms. They involve specific algorithms that perform calculations such as those for solving systems of linear equations, finding roots of polynomial equations, or approximating integrals. Many algorithms are iterative, meaning that they repeat a series of calculations until a desired level of accuracy or convergence is achieved. For examples, include the Newton-Raphson method for root finding and trapezoidal rule for integration. The last technical description is the software implementation. Numerical methods are typically implemented in software packages or programming languages that allowing for efficient and automated calculations. This is because numerical methods often involve repetitive, complex, and precise calculations that are best handled by computers. Tools like Python, MATLAB, and scientific libraries make these methods accessible and practical for real-world applications in science, engineering, finance, and education. Now I will present about theoretical description. There are three theoretical descriptions which are error analysis, stability and convergence, and efficiency and complexity. The first theoretical description is error analysis. Theoretical analysis of numerical methods involve understanding and controlling errors which arise from discretization, approximation, and finite precision calculation. By analyzing these errors, we can assess the accuracy, stability, and convergence of numerical algorithms. This ensures the results are reliable and help guide the selection and refinement of methods for solving real-world problems effectively. The next theoretical description is stability and convergence. Key theoretical concepts include stability, which is the method resistance to amplification of errors. Without stability, even a convergent method can produce useless results if minor errors become amplified. A convergent method guarantees that, in theory, you can achieve any desired level of accuracy by refining the step size. A stable method ensures that small errors don't amplify over time, while a convergent method ensures that refining the method leads to a more accurate results. The last theoretical description is efficiency and complexity. The efficiency of a numerical method is often measured by the number of computations required for a given accuracy and its complexity by how it scales with the size of the problem. Efficiency refers to how quickly and economically a numerical method can achieve a desired level of accuracy. Complexity describes how the computational cost of a method increases as the size of the problem grows. Together, these concepts help evaluate the practical performance of numerical algorithms and guide the selection of suitable methods for real-world applications.
Solving a confusion. This is our question. Because of maze one candidate is not just horizontally instead is called time according to Newton's law. In the air resistance acting on sphere depends on its surface temperature in Celsius. In the calculation, we are using two methods. One of the methods is a Gauss method, and the below one, yn plus 1 equal to ym plus hftn yn. This is the formula of Gauss method. And also the second method is Rajputta method. This is the formula of Rajputta method. Yn plus 1 is equal to ym plus h over 6 k1 plus 2 k2 plus 2 k3 plus 4. After we counting n equal to n 0, 1, 2, and 3, we will get k1, k2, k3, and k4 using the form. And then using the first one, yn plus 1 equal to ym plus h over 6, k1 plus 2, k2 plus 2, k3 plus 4. We sum all the k1, k2, k3 inside the form and we will get the final answer. The below one, t not equal to 100 and t equal to 25, and then k we use 0.1 minute, and h we use 1.0 minute. This is the data we use during the calculation. In this slide, show that the manual plan and also we we do the we using the application of model page to do the coding. In the first picture, we can see that we use the formula that just now we showed as t m plus 1 equal to tm plus hm tn yn. We use this one and then we count it into four terms. That then we will get the answer. And then the second one, we can see that using the application dynamic recording, we just key in all the information that like just now I have said that the T we use 20 and then T the T not we use 20 to 200 and then T we use 25 K we use T we use and then H we use and then n equal to 3 means that we will count 3 terms and then the T naught because it's given is 2 and then we will count another 3 terms and then this is the result of it and then we get using coding. And this one is we the slide is shown that we count it in manual. Just now we have said that we use 3 to count it, so we have 3 terms. And this one we got another 3 to 1, 3. You can see that the first one. Each term we will count 4 terms like K1, K2, K3, K4. And then after that we use the formula to sub all inside and then we will get a T. We already count 3 terms and this is the manual calculation of this method. And then this slide is show that the coding calculation which we use the application programming key in order value and then we will get it. The answer, the result of Roach-Kutta method is totally same with the manual that the calculation we do by manual. So this is the coding calculation.
In terms of real-world applications, this type of modeling is highly relevant across multiple fields. Firstly, in mechanical and aerospace engineering, it helps simulate heat dissipation in projectiles and during spacecraft re-entry. Secondly, for thermal system design, it's useful in predicting cooling efficiency where lab testing is not practical. Thirdly, in material science, we can analyze heat flow during manufacturing processes. And lastly, and in environmental science, it supports the simulation of heat exchange in climate models. Last but not least, when it comes to choosing a method, Euler's method is useful for quick, low-cost estimates, especially in embedded systems with limited processing power. And for more precise simulations, Runge-Kutta RK4 is preferred particularly in fields like CFD, finite element analysis and control system where accuracy is essential. Euler's method is simple and easy to use, but it becomes less accurate with larger step sizes. Over time, the results can diverge from the expected outcome because it only uses the slope at the current point. As a first-order method, its errors directly proportional to the step size. Runge-Kutta method RK4 produce much more accurate results by averaging slopes at several points within each step. Its error is proportional to the step size to the fourth power, making it far more precise. Although RK4 is more complex, it was manageable with tools like Python and MATLAB. From this project, we learned that numerical methods vary in accuracy and complexity. Choosing the right step size is critical, and RK4 is better for simulation that need high precision. Overall, the project showed the need to balance accuracy with computational efficiency in real-world applications.
For carry out this project, we have group meeting. This is the summary of our group meeting. We can see that on May 30, we have start to discuss all the topic of assignment, and then we go to the fees and then discuss with the what is the title we use and then the author had taught that we how how can we use the application programming to insert all the coding of our assignment. And then we also have distribute each part of each other and then we also have complete part using two methods just now I had mentioned it. And then uh, I I am in charge to do all the manual part in during the lecture class and then I had take a look for teacher for lecturer for checking. Last we also have finalized and also do final checking for our work. This picture is about our discussion. We we carry out the discussion in the study room in college and also we also have discussion through